Welcome. Thank you for attending our session. So let's just do a quick round of intro and then we'll get started. I'm Sujoy Sen. I work at Google.
Vishal Jain from Nvidia.
I'm Bhushan Mehendale from Microsoft.
Rajat, Microsoft.
All right, let's get started. So today we want to talk about standardizing firmware update for GPUs in a hyperscaler environment. And so we'll go through a little bit of a background. We kicked off this effort with the CLA amongst the three companies, and now Meta and AMD have also joined. And we have 3 work streams. This is the 3rd work stream. There were 2 presentations on the other 2 earlier this morning. Then dive into what the firmware update workstream goal is, specifically what the scope is, the capabilities that we are defining, and then Rajat has an exciting demo on the compliance tool, which is pretty cool, and then we'll finish up with a summary. So the reason we are here and we started this work is because of 2 letters, AI. Some of you may have heard of it, and GPUs are sort of play a central part in this explosion of AI. So consequently, hyperscalers want to get GPU products out there as soon as they can, right? As soon as these products are available from the suppliers. And in order to do that, they want the integration of these GPU products into the hyperscale solutions to be as seamless as possible, right? To be as frictionless as possible. And on the GPU supply side of things, they're really looking for a more uniform set of requirements that they can develop their products to. Makes it a lot more efficient and quicker to develop the GPUs. And also this allows them, they would like to essentially deliver something that's ready to be integrated out of the box. So these 2 requirements are very complementary, essentially addresses the same pain points. So we got together and we sort of discussed this, and we realized that, well, standardization is probably one of the big tools here in our toolbox to go address this. And we're at OCP. This is sort of preaching to the choir, but if we can standardize some of the non-differentiating elements of this, from a vendor perspective, they can build a chip or build a product and supply to different hyperscalers because we have harmonized the requirements. And similarly, hyperscalers can sort of ingest and integrate products from different suppliers. So before we get into standardization, right, we have to first decide and agree amongst ourselves what the model is that we are going after, right, in terms of what are we going to standardize. And we sort of came up with, and if you've attended the previous 2 talks earlier today, you would have seen a similar picture. Essentially 3 elements, right? The hyperscaler fabric, that's sort of the orchestrator, if you will, or data center services, talking to a BMC on a host, presumably using Redfish, and then the BMC talks to the GPU subsystem. And then from a GPU subsystem standpoint, we have 2 models, the UBB model, the Universal Baseboard model, which is essentially something that comprises of 1 or more GPUs, but also other components. There could be FPGAs, PCI switches, fabric elements, and all of that is fronted by what we are just calling accelerator management controller that exposes Redfish. The other GPU device model is a discrete model. Think PCI add-in cards, but it's not restricted to just a PCI add-in card, but it's easy to think of it that way. The main idea there is it doesn't expose Redfish, but it exposes MCTP, PLDM over like an I2C USB management link. So now that we have an architectural model in mind, why did we choose firmware update as a work stream or a pain point to go after? Well, the answer is simple, because firmware update is a very critical operation in a data center, right? Especially for hyperscale environments where we're dealing with a huge volume of these systems. And firmware pretty much either makes or breaks the product, right? It delivers stability, performance, security, and If firmware update doesn't go right, large parts of systems, large parts of the data center can be down. So this actually is a very critical, sort of mission critical operation. So it's very important that we define, what the expected behavior is. So from a scope standpoint, it includes any mutable components within the model that I just described, not just the GPU firmware, but anything else in the subsystem that requires, that is mutable. And apart from just defining the interfaces themselves, Redfish, PLDM, we've focused a lot on defining the capabilities, essentially set of requirements that, a GPU subsystem needs to adhere to in order to support sort of seamless firmware update, right? And to talk more about that, I'll hand over to Vishal.
Thanks, Sujoy. So, like Sujoy said, right, as a vendor, we get set of requirements like support seamless firmware update. But who knows what is seamless, right? How do we define seamless? The other set of requirements we get is thou shall support secure firmware update. The devils are in details, which is what we walk through as this process to dot every I and cross every T to articulate what security requirements would be, what impact requirements would be. So if you refer to the spec, we have clearly articulated what requirements lie for firmware signing, right? What update time SLAs we should conform to. Is it 5 minutes, 10 minutes, 15 minutes, or an hour, right? And also, how do we define disruption? I have a slide following to this one, which will show you the vulnerability of disruption when we do firmware update, right? It's we have fine-tuned the steps and stages to reduce that window to a bare minimum. We also have articulated what rollback and anti-rollback really means, right? What is an acceptable posture of anti-rollback behavior that a hyperscaler would agree to, right? Firmware image formats, right? If there are multiple firmwares, which could be in a range of, say, 10 to 30 in a UBB case, what should be the requirements? Is there a top limit to the firmware image size that we can push to a BMC, right? What should we package all of these images in a single, logical construct, which will be a PLDM construct or like a zip file? What is acceptable? Should this package be signed again to meet the security requirements, right? From resiliency and redundancy point of view, what should be the behavior when a single image gets corrupted, right? Should it automatically fall back on the on some backup image, right? Should we support active, inactive image, golden image versus an working image? All those kind of things we worked out, right? We also nail down requirements around recovery, what recovery actually means. Does it apply in single fault scenario or only in double fault scenario when both images or all images on a device go corrupt, right? So this document captures all of the requirements so that we can, as a vendor, work through them and deliver the product that hyperscaler would agree to. If you look at this picture over here, a lot of things to, I'm not sure if my mouse is not visible here. Right, okay. Okay, awesome. So if you look at this picture, we took a orchestrator mindset when we came up with the standardization, right? And hyperscaler does not perform firmware update blindly, right? It goes and probes the fleet to find out what is actually there, how much time firmware update would take, which components would be touched when you do firmware update. All of those workflows are captured in this pre-check, which is non-disruptive to GPU at this point, right? Even there are use cases where hyperscaler A would say, I want one-shot firmware update, meaning I push a bundle to you, You take the bundle, apply the thing, make it ready for activation, and then give me the control back. There will be an hyperscaler would say, I want to I want to be opportunistic. I want to push the image to device, but not arm it until I decide I want to arm, because for whatever reason, I want to push the image at the device EEPROM and make it ready, right? So we created so based on PLDM, we came up with these stages, which we call copy, arm, activate. Copy refers to the fact that you are updating EEPROM, right? Arming is, when you're telling the device that, yes, the image that I just copied, you can boot from that image next time when you reset or when you're starting to fetch the code from EEPROM. Activate is actually firmware load trigger, which is the physical step of reset or power cycle that causes the device to start fetching the firmware. So all in all, if you look here, oops, GPUs in this case, right, is operational at all time. It is in service all along copy and arm steps. We don't have to take GPU out of service when you are updating the flash, when you are arming the flash. You have, GPUs can even withstand resets while all these operations are going, because because of the way it is, the firmware update specification specifies it should handle the images, right? Here, you can also see how orchestrator steps are mapping to firmware device state. Firmware devices, again, you can think of it as a component within GPU, which is updating, which is managing the image states, right? So, like I said, security is at the front and center of all firmware update these days. So, the firmware device needs to not only download that image, it has to verify it before it goes and updates the device EEPROM with the image, right? And once it is done with verification, it applies it and gives a state which probes the BMC or whoever is the update agent to find out, shall I arm it, so that next time you reset me or give me a trigger for a reboot, I go and boot off from the other device, from the other slot that you just updated from. So all in all, we are seeing a disruption only when you are activating the firmware, which is this step where you provide a reset or a reboot to GPU. It causes a downtime to GPU. The fact that you are updating the EEPROM does not take GPU out of service. The fact that you are arming it, meaning making it ready for boot with the new firmware, does not take GPU out of service. So these states help us as vendor to satisfy both use cases. One-shot firmware update where no hand-holding is required. You just push the image. All the images on UBB baseboard get automatically updated by virtue of handshake between BMC and firmware device here. And also, if you wish to stage it, the image in device EEPROM, you can do it by excluding the ARM step, which you see over here. Having said that, I'll pass it on to Bhushan for compliance tool to showcase what we have done.
Thank you, Vishal. So one of the founding principles of this particular effort was to make sure that we just don't create a bunch of specs and push it out, right? We wanted to make sure that there is an easy avenue for both vendors and suppliers, as well as hyperscalers, to understand and measure how compliant we are to the specs, right? So with that in mind, one of the early steps that we took was creation of something we call as the compliance tool for accelerator management, right? Which we call as CTAM. We decided to base this on the OCP DIAG effort, which is a very well-known standard and a specification that the test and validation subgroup, a special subgroup within OCP has, right? And as a part of this, what we did was we took the spec and we created validation or sort of rather compliance test to the specs, right? And at present for firmware update, the telemetry and health as well as the RAS of the GPU systems, we have tests in place, right? And for firmware update, as you can see, we have 22 compliance tests in place. And these are the things that both suppliers as well as hyperscalers can run. And these are runnable on both Windows and Linux. These are platform agnostic to the best capabilities. Again, all of this code in the true spirit of OCP is available online for you to get. You can follow this URL. We absolutely encourage you to contribute to this, take a look at it, and give us feedback. So with that, let's jump to a quick demo that Rajat, my friend over here, will give.
Thanks, Bhushan. All right, let me just steal some time. I'll get the demo started. So, I'd like to re-emphasize on what Vishal just said, right? The devil's in the details. You start with those devilish details, you build requirements. From the requirements, you build the use cases. From the use cases, you have the test cases, right? So the compliance tool, like any other validation tool, yeah, it is a framework, and it has a bunch of test cases as well, right? So in here, I'm just trying to list down what all the test cases you have. At any point of time, you can easily add more test cases, and it will discover all the test cases on the fly, right? The kind of test cases that you have are broken down in as per the work streams that we had talks on today, right? You have the firmware update work stream, the telemetry work stream, and you have the RAS work stream. So if you just look at the firmware update work stream, we have a bunch of negative test cases, bunch of positive test cases. Negative test cases are the ones where you want to make sure that it's actually responding properly, even if you have some errors, and as defined again by the firmware update spec, right? So in this case, we're just going to pick one positive test case for now, and we can select either by the test case name, or you can select by the test case ID. You do need to specify which workspace you want to get all the collaterals from. The details of the collaterals are there on the bottom right there. And in this case, we're just picking one simple firmware update test case, right? It does a full device update wherein it goes ahead. You have the full bundle. The management controller then breaks it up into the respective components, and then it flashes it to those places. So just done a fast-forwarded demo here. It's gone ahead, done the full bundle update, and it's got a pass in this case, right? What you also have is coming to collaterals, right? On the bottom right, there are some. We are trying to reduce this as we speak right now, where we may have lesser and lesser dependence on a vendor to actually push all these collaterals. Like, say, for example, a negative test case that we are calling out here, right? We are trying here in this case, we are trying to do an invalid signed image. Obviously, we expect it to fail, and it does. In this example, yeah, we just call it by the ID, and fast forward, it does fail, right? So our immediate next step is to see what we can do to reduce those dependent collaterals. Can we be more discoverable in nature? Can we be more auto-generative in the whole flow of the framework test? Okay, and I'll just give it back to Bhushan now. Thanks.
So quick call to action. We've made tremendous progress in the last 9 months. We started this effort as a collaboration between Microsoft, Google, and Nvidia. We're very excited to have AMD and Meta on this effort. You can find our current spec at this particular URL. Absolutely, feedback is welcome. You can also get in touch with us using this particular email ID. There is a bunch of ongoing work as listed over here, and your help and feedback would be really appreciated. Thank you so much. I'll open up for maybe a minute of questions, and then we can stop. Thank you.
Okay, I'll take one question. So before you have trying to submit this one to, work stream in the open system firmware, right? Is still your plan? Yeah.
Yeah, so there was an ongoing conversation between the hardware management and the the OSF work group, essentially. To us, it really doesn't matter as long as it has
So
a
right
good
now
home,
it's
but that's something we can absolutely work on.
okay, so right now it's a work stream over there, or just
What is it, sorry?
right now it's a work stream in the hardware management.
Yeah, it's currently as a part of hardware management, but there isn't really a final place for it. We are just doing this under a CLA, but we're absolutely, more than happy to put it in whatever the right place for it is. Yeah.
Okay, thank you.
One more question, maybe?
Yeah, one
Yeah, go.
quick question. What is the activation time to upgrade a GPU? And is it different for one GPU and like 8 GPUs?
You want to take that one?
So, like I said, right, you have to view firmware update from a slightly different angle, right? Previously or traditionally, we take GPU offline, we update the firmware, and we bring it online, right, after reset. Now, you can update GPU firmware while it is in use. So the activation time is limited to GPU reset time, right?
Oh,
so
only reset, right? Only resetting the GPU
right.
when the OS is running.
Either that way or depending on implementation, right? If your OS can handle GPU going offline, you can reset it while it is up and running.
Okay, thank you.